Okay, so is it better now? Can you see it? Okay. So, one of the things I realized from the lecture yesterday is that, there are certainly challenges to give this remotely, and those interruptions cost us some time. So even though I had an ambitious list of topics that I was going to cover, I think the reality is we're going to, not be able to cover all of it. It's better to cover less and go a little bit deeper into those topics. So I'm going to focus today's lecture on understanding nuclear interactions and theories of neutron-rich matter, and then talk about neutron star masses and radii, and discuss what we've learned about neutron star structure from observations. We'll discuss, more interesting phase transitions at high density in the next lecture. So I remind you, in the last lecture, we covered some aspects about, very elementary aspects of statistical mechanics and quantum many-body problems. We discussed how matter transforms from being, this heterogeneous mix of nuclei and electrons into a mix of nuclei, electrons, neutrons, and then eventually makes a transition to a state of matter which is a liquid of neutrons, protons, and electrons. So in the last lecture, we discussed the neutron star crust. In today's lecture, we'll discuss the outer core of the neutron star. So this is what we discussed last time. We learned that when matter is compressed to high density, the nuclei become more and more neutron-rich. Eventually, there you reach a point where neutrons drip out of nuclei, and that's the outer crust and the inner crust of a neutron star. Okay, and these are called neutron stars because of this very rapid increase in the neutron fraction as you increase the density. Okay, so the outer core of the neutron star, that's the region between about 10 to the 14 grams per centimeter cube in density, and about, say, 6 or 7 times 10 to the 14 grams per centimeter cube. That is a region of the neutron star that's very interesting. It's interesting because we think we can now describe the equation of state and properties of that matter using our knowledge of nuclear physics. It's also interesting because it's actually a large fraction of the neutron star by mass. This is the part of the neutron star that contains a significant part of the mass of the neutron star, and it also has, as we will later see, a very important impact on the radius of a neutron star. So even though the inner core of the neutron star is interesting in many respects, the outer core of the neutron star plays a very important role observationally. And we'll discuss that in the lecture today. So if we want to describe a system consisting of neutrons, protons, electrons, and muons, we need a theory that describes the interactions between neutrons and protons. In fact, it turns out that the neutron fraction of this outer core is so large that to first approximation, we can even just consider this matter to be composed entirely of neutrons. So the typical neutron fraction is, of the order of 90 to 95%. So having about 5% protons can be important for some aspects, but for properties like the equation of state, it's a very small correction. So if we want to describe the outer core of a neutron star, we really need a theory to describe dense gas or dense liquid of neutrons. Okay, so to understand, of course, nuclear interactions, we have to start with something that's fundamental. We know that the fundamental theory of strong interactions is one in which quarks and gluons are the fundamental degrees of freedom. And the QCD Lagrangian is very simple to write down. You can basically look at the elementary degrees of freedom, the quarks and gluons, And the coupling between the quarks and gluons is given by the gauge principle. And unlike electrodynamics, this is a non-abelian theory, which means that there is more than one type of exchange particle. And these gluons come in several colors. The quarks have these charges called colors, and they come in 6 flavors and 3 colors, as indicated by the diagram there. And there are very interesting vertices between the quarks and the gluons that are all very simply described by this covariant derivative, which is shown here. Which tells you that there are these SU3 matrices TAs, and there are these gauge fields labeled by the index A. So this Lagrangian looks incredibly simple, but it's really difficult to solve at low energy. And the reason it's very difficult to solve at low energy is because it requires a non-perturbative method to solve this field theory. So although it's, so far we haven't been able to solve QCD at low energies or low temperatures, either in lattice QCD or in analytic theories. However, as I mentioned earlier, and I'm sure other lecturers have discussed, at very high energy, so which high energies can be achieved either by increasing the temperature to very large values or the density to very large values, then of course the coupling constant, which is shown in the lower graph here, gets smaller, and at some point it gets small enough so that one can do perturbation theory, in which in any physical process, you don't need to impose or include arbitrary number of interactions between quarks and gluons. Just a leading order correction or next to leading order corrections are adequate. However, we are interested in neutron matter at low density, at relatively low density. And under these conditions, we know quarks and gluons are not good degrees of freedom. That's because all we see in the physical world are neutrons and protons. So we need to be able to describe these confined states of quarks and gluons, the nucleons, and describe their interactions. So the two things we know from QCD that are important in any nuclear description is, of course, one, that there are all these color singlet objects, and the leading order interactions between these color singlet objects are going to come from fluctuations that are very complex from the point of view of QCD. And the second important piece of physics that we need to account for when we do low energy interactions between neutrons is to understand that there's something interesting about QCD, in that the masses of the quarks that appear there are very small compared to all the other scales in the problem. Really, there's only one fundamental scale in this problem, in the QCD Lagrangian, that's the quark masses. But there is this phenomena of non-perturbative physics which generates a scale in QCD called lambda QCD, and we expect lambda QCD to be of the order of a few hundred MeV. So the light quarks are the masses of the light quarks are very small compared to this typical non-perturbative scale in QCD called lambda QCD, and for that reason, we think that chiral symmetry, a symmetry of the Lagrangian when you ignore the masses, is a good symmetry of the theory. And when you have QCD at low density or at low temperature, we know that this chiral symmetry is spontaneously broken by the vacuum. So whatever we do, we need to account for these two facts when we describe low energy interactions between nucleons. So let's get started with trying to understand low energy interactions between baryons. So of course, from our experiments, we know that baryons and mesons, there are lots of baryons that we see in experiments. In addition to neutrons and protons, we see baryons that contain strange quarks called hyperons. We, of course, see mesons like pions and mesons containing strangelets like kaons. And we also know from experiment, just by scattering baryons off of each other and doing experiments in which you produce mesons, that these interactions are pretty complex, and they're also very short range. This is something we know from experiment. We also know that the pion is the lightest of the mesons, and in fact, it's lighter than the other mesons by a large amount. So its mass is only about 140 MeV. Most of the other mesons that we see are significantly heavier, and we understand why that is the case. And that's the case because pions are goldstone bosons that arise when you break a symmetry. In general, whenever you break a symmetry in the ground state, there are some very low energy modes called goldstone bosons. I'm sure you've heard about this. And these are the lightest particles that are in the low energy theory. So the lightest particles that can be exchanged between nucleons will give rise to the longest range force between nucleons. Clearly, in the hadron spectrum, there's a lot of other mesons that play a role. I'm guessing that in some of the lectures you heard on finite temperature QCD, for example, when you do heavy ion collisions, when you get to high temperatures, you produce all of these heavier mesons in addition to the pions. There is a whole tower of mesonic states. For example, there's an omega meson, there's a rho meson with masses of order 800 MeV. These are significantly heavier than the pion. So there are many of these states. So if you think about exchanging these heavier states between nucleons to produce a force, it gets very complicated quickly because there is no clear separation between these heavier meson states. So it's not useful to just think about nuclear forces as arising due to the exchange of pions and a set of heavier mesons, because this collection of heavier mesons, there are many of them, and there's no systematic way of accounting for all of them. So then we are faced with the question, how can we write down a theory of strong interactions between nucleons if we don't have very well-defined exchange particles that we can include in calculating the interaction, which is what we typically do when we write down a field theory for interacting fermions. So in the past 50 or so years, there have been two approaches. The old approach is called potential models, where you just write down a potential for the interaction between nucleons as a function of the distance between the two particles, or in momentum space as a function of momentum. And a more modern approach in the last 15 or so years has been to use an approach called as effective field theory for low energy nuclear interactions, which we shall briefly discuss. Okay, so are there any questions about what we just discussed so far? Okay, if there are no questions, let's proceed. We have the lightest particle that we can exchange between nucleons is the pion, and the pion is a pseudo-scalar particle. So if you have a pseudo-scalar particle and you want to write down the interaction between nucleons and the pseudo-scalar particle, you have to respect the basic symmetries. One, of course, the basic symmetries always are the Lorentz symmetries of a theory, and the other symmetry here we want to respect is chiral symmetry. And if you took those two things into account, you find that the pion-nucleon interaction that you can write down in momentum space in second quantized form or in terms of these field operators is given in the first line. So the first term is just the kinetic energy. It's the energy of non-relativistic nucleons. And the second term that you see, proportional to Ga over F pi, is the coupling of the pions to the nucleons. So if you look at the structure of the interaction term between pions and nucleons, you see that it depends on the internal quantum numbers of the nucleon. It has a gradient of the pion. This is a general property of any Goldstone boson that couples to fermions, in that only the gradients of the fields associated with the Goldstone bosons can couple to fermions. And you can see immediately that the gradient coupling to the pions is going to lead to interesting structure in the pion potential. So from the Lagrangian, if you were to say, let me now calculate what is the potential between two neutrons or two nucleons that arises due to the exchange of a pion. That is shown by the Feynman diagram on the left, where you have a pion exchange, and the pion exchange gives you a momentum space potential, which is given by the expression on the right-hand side. So when you look at the expression on the right-hand side, it looks very simple. It looks like it's got a tau1 dot tau2, which tells me that the pion exchange depends on the isospin of the nucleons, where tau1 and tau2 are the isospin matrices. And it also depends on the spin of the nucleons, which is sigma 1 and sigma 2 are the Pauli matrices for spin associated with the nucleon state. Now, what's important is also to recognize that there is a momentum in the numerator of the potential term. And the denominator, which is q squared plus m pi squared, this is what we expect for any Yukawa force in momentum space. Whenever you exchange a particle, the potential in momentum space goes like 1 over q squared plus m squared. But now we have this q squared in the denominator. Okay, so we should expect some important differences from just the Yukawa potential, in which you don't have a q squared in the numerator. So now let's just do a Fourier transform of this potential. And if you do a Fourier transform of this potential, then you will get a potential in coordinate space, and that's given in the line below. There's a typo there. It should be v pi of r. So that's the potential as a function of r, where r is the distance between the two nucleons. So when I write this in momentum space, you begin to recognize the troubles that are going to arise because you have a q squared term in the numerator. So again, the spin and isospin structure is explicitly written. So what you see is that in coordinate space, there is a term that is proportional to S12. S12 has has the properties of a tensor, and it's written in the line below, where it couples spin and the coordinates. So it not only depends on the spin, but it also depends on the orientation of the spin with respect to the coordinates R1 and R2. What is more significant is to notice that there is a Yukawa-like term, which is e to the minus m pi r over r. So that is something we are very familiar with. Whenever you exchange a heavy particle between fermions, you get a function like that. But in addition, you see that there are terms that are proportional to 1 over r squared, and there are terms that are proportional to 1 over r cubed. There is also a term that is a delta function in radius. So what this means is that at very small r, when the distance of separation between the two nucleons is very small, this interaction is very singular. So if you were to just take this potential and try to solve the Schrodinger equation, which we would like to do to describe, say, the scattering between two neutrons or the binding between two neutrons, a neutron and a proton, you will immediately encounter infinities. So you cannot solve the Schrodinger equation directly by putting in this potential. So that's a really interesting problem, but it is a deeper problem in general, because whenever you want to describe effective interactions, you're going to have to describe the interaction between two particles at long distances. But when you want to solve the Schrodinger equation naively requires you to know the potential everywhere. So this is a problem that we deal with using renormalization methods. But the fact that we have a pion exchange potential that is very singular at the origin means that it cannot be the whole story. So this means that even though the pion exchange is the most important long-distance force, whenever we want to solve a quantum mechanics problem, we really need to also understand what's going on at shorter distances. And if the potential is singular, it means that the short distance physics is actually essential even at low energies. Okay, are there any questions about this? Okay, so if there are no questions about this, let me see if I can, 1 second. Let me now move on to discussing these low energy, short distance aspects of the nuclear force. Now, we just discussed that even at low energies, the interaction between two nucleons requires a prescription of the forces at small distances that are small compared to the Compton wavelength of the pion. So here's on the right-hand side is a cartoon showing the nucleon potential as a function of radius or distance between the two nucleons. So when the distance is greater than about one Fermi, the important interactions are coming from pion exchange, because all of the other potential excitations in the QCD, like omega mesons and rho mesons, are much heavier. But we still need to provide a description of the forces at short distances, because otherwise the pion exchange is too singular to understand. So what this means is that in principle, there is a potential at short distances that is going to play a role, and we need to determine those forces using data. So usually you use the data that we have from scattering two nucleons. We have very good information about nucleon scattering data, the scattering between a neutron and a proton, two protons, etc. And we measure something known as phase shifts from measuring the cross sections. So these phase shifts provide useful constraints on the nucleon potentials. So models that try to fit the phase shifts show that at short distances, there is a lot of repulsive force between the nucleons, and that these repulsive forces are essential in addition to the one pion exchange forces that exist at short distances. So the other thing that we also learn from these fits to the data is that the range of the short distance forces is actually comparable to the size of the nucleon. So the nucleon is not a point particle, and defining the size of a nucleon is actually not a well-defined question. If you think about the charge radius of a nucleon, the charge radius of a nucleon, like a proton, for example, is about 0.6 Fermis. So if we just use that as a simple measure of the size of the nucleon, then you see that the nucleon, treating the nucleon as an elementary particle becomes problematic, and so when the distance between two nucleons is very close. So if the typical distance between two nucleons is of the order of 2 Fermis, then it's not a bad approximation to ignore, to not explicitly account for the intrinsic size of the nucleon. But as you go to high densities, these nucleons begin to get closer, and at these higher densities where the distance between nucleons are very short, then clearly, as we discussed. Okay. So we continue, and so I was just telling you that the nuclear force at short distances is important to include in addition to pion exchange when we study nucleon interactions, even when the energy of the nucleons is very small, and that's something that people outside of the nuclear physics community don't always appreciate. The importance of short distance forces, even when the energy of the neutrons is very small. So in principle, if you just want to calculate the scattering cross-section or the scattering phase shifts using a nucleon potential, you need to specify what the forces are at short distances. So here's an example of a potential between nucleons that is obtained by fitting to all of the data available on nucleon scattering. So you can do scattering of nucleons into various partial waves, S waves, P waves, etc. You can do you can study the polarized scattering of nucleons in which the spin of a nucleon is aligned with its momentum. So you can do you can basically study the partial wave and the spin aspects of the nucleon-nucleon scattering. And what people have done is they have built models for this potential where the structures in the potential, in addition to just the distance between the nucleons, depends on the internal spin and angular momentum components of the two nucleons involved. And so there are these potentials like argon 14, 18, etc., which include very large number of these spin, angular momentum, and tensor operators, which is shown by this by the expression where you have a radial function between which is denoted as Vp, which tells us how the radial, how the force depends, or potential depends on the distance between two particles. And then there are these operators that act on things like the spin and the angular momentum of the incoming pair. So, for example, the simplest of these would be to just take the central potential, in which you ignore the spin and the tensor components of this potential, and you see that's denoted by this black curve in the bottom figure. And if you look at the black curve in the bottom figure, it looks like it's got a very strong repulsive component at short distances. It's got an attractive component between about 0.6 or 0.7 Fermi and out to large distances. So that's the most important central component of the force. There are other forces that seem to have attractive components at short distances. But the most important force in between nucleons, for example, in neutron matter, will come from the central component of these forces. Now, the functional form of this potential at short distances is not given to us by any fundamental theory. This is just a guess. We would like to describe a force whose shape, or describe a potential whose shape is determined by pion exchange for radius that is large compared to, say, 1 Fermi. But at short distances, we have no guiding principle. So we basically can choose many different functional forms to fit the scattering data. And this is one such potential, and that's why we call this a model. A model is something where it describes the data as well as we can, but there's no fundamental justification for the use of certain functions. And the use of these potential models has been incredibly successful. We've learned a great deal about nuclear structure from using these potentials, but it has one important drawback. The important drawback is if somebody was to ask you, how does the answer change if I was to use a slightly different potential function at short distances, estimating the error because of different possible short distance behaviors of the nucleon-nucleon force becomes very difficult to do in practice. So one way to deal with this, of course, is to say, let me construct a handful of models with different short distance behavior and see how different the answers can be. But there's a better way to do it, which is what is called effective field theory approach to understanding the dependence of low energy properties on the details of the short distance physics. Okay, so that takes me on to talking about making some general comments about the potential. In classical mechanics, of course, we have a physical understanding of what a potential is. The potential force has an impact on the motion of particles, but in quantum mechanics, potential is not an observable. You cannot do any experiment just to measure the potential. What you always measure is a combination of the kinetic components of the interaction and the potential components of the interaction. So that together is what you measure. So you can use very different potentials to get the same low energy physics. And what people have done in the past is to make some reasonable assumptions about the about the short density, the short distance physics to solve the Schrodinger equation and fit observables. That's what we just discussed. But maybe the assumptions at short distances lead to large errors. We don't quite know that a priori when we do a potential model. So what one does is try to come up with a systematic way of accounting for short distance physics. And so effective field theory, I'll give you a very heuristic introduction to effective field theory. The basic idea is to characterize the short distance physics in the most general way. And this is how one goes about doing this. So suppose you had a potential between two nucleons from the exchange of an omega meson. You would write down the potential in momentum space by the line given there. The full potential is given by g squared divided by the usual denominator for heavy particle exchange, which is q squared plus m squared. So now, if I knew that this was the potential and I was doing a scattering experiment at low energies, what I would do is I would say, well, if the typical momentum exchange between the nucleons is small compared to the mass of this heavy particle, why not just expand this function in a Taylor series, and I would get a leading term, which is what would be g squared over m squared. So that would be a contact interaction. And then you would have a next order term, which is of order q squared over m squared. And that would be an interaction that depends on the momentum exchange between the particles. And so you can continue this expansion, Taylor expand the full potential in terms of this. Now, if you had many exchanges, and if all of these exchanges contain very, very different mass particles, but all of these masses were of the order of, say, a GeV, then you would say, well, I have a whole bunch of heavy particles that can be exchanged, but I don't quite know how to include all of them into the potential. You could just say, let's think about a short distance potential which is an expansion very similar to this, what we had for the omega meson exchange, but one in which we have some general coefficients, C0, C2, etc. And there is a scale that's associated with heavy particles, which we'll just call lambda. We don't know what that scale is a priori. But if we found that most of the heavier particle exchanges were around 800 MeV to a GeV, say for nucleons, then we can assume that the scale lambda will be of order 800 MeV. But we don't know that a priori. So instead of having a model, you can have a general expansion in terms of these momenta, where C0 and C2 are called low energy constants. Okay, so this now we're trying to get away from any kind of model dependence. We are just trying to figure out if there is a hierarchy of scales. As long as lambda is large compared to q, there should be a general expansion of this sort. So this is the basis of constructing low energy effective theory, where you replace some assumptions about what types of particles are being exchanged by low energy constants and a general momentum expansion. Now, the other part of the problem that's important in describing nucleon-nucleon interactions is to appreciate that nucleons are not point particles. So what happens, even for example, when they exchange pions, is that a nucleon can exchange a pion and go into an excited state, say a delta meson, delta baryon, which is shown in the figure on the left. So in quantum mechanics, of course, you can have virtual states with large energy. So the for example, you can start with two nucleons at low energy. They exchange a pion. One of the nucleons becomes a delta. Of course, this is off shell in the sense that it's a high energy excitation, and it, on short time scales, you violate the total energy of this system, and you can create a virtual state with a large energy, of order 300 MeV for, say, the nucleon on the delta. Now, at low energies, this virtual excitation, we can't resolve it because it's occurring on such a short time scale. So in principle, instead of trying to write down a theory in which you have to worry about how the delta couples to the pion and the nucleon, you could do the same. You could have the same strategy as we did for the exchange of mesons. You could just say what happens is given by a coefficient in which two pions couple to a nucleon. So in other words, this heavy particle delta that is propagating between the two pion states, we don't know if that's the only state available for such a transition. So why not just call it a constant, a low energy constant that couples two pions to a nucleon and fit the two pion single nucleon interaction directly. So that is the other important aspect of trying to write down an effective theory, is that you start generating these coefficients that couple, say, two pions to the nucleon, and that two pion nucleon coupling can then be determined by fitting, say, pion nucleon scattering in a low energy theory. Now, this interaction between two pions and a nucleon, you can now see that it's going to start generating interesting three-body forces, for example. Now, in addition to two nucleon forces, there are forces that are unique to three nucleons. So in the bottom, you see, for example, that you have three nucleons. The three nucleons can exchange pions. And in general, you could have thought about the exchange between a pion between any pair of nucleons as a sequential process. So that would just be a two-body interaction between three particles, and that's not new. However, when you have these intermediate states that are not accounted for by the theory, so remember, we are trying to write down a theory of interactions between nucleons. We don't want to explicitly include all of the heavier particles like the delta. In such a theory, of course, this is not a two-body interaction. This is really a fundamental three-body interaction. So this three-body interaction can arise due to two types of terms. For example, you had the two pion single nucleon coupling term, which gives rise to a force that also appears in the two nucleon sector. That's the two pion nucleon coupling in the first diagram on the right-hand side. But it also leads to short distances, interactions between three nucleons at short distances that you would write down again in terms of just a contact interaction, like we did for the two nucleon interaction. So what all of this is that there is a physical basis for expanding the Hamiltonian as a set of operators. Each operator is defined by the dimension. In momentum space, you can think of each of these operators as containing more and more powers of momenta, just like we saw here, for example. The first term had no powers of momentum in it. The second term had powers of momentum in it. So in general, when you go to, when you think of the Hamiltonian as a sum of all possible operators, some of them contain some number of fields, some of them contain some number of derivatives of the fields, but we just look at the momentum content of the operator and the dimension of the momentum, number of powers of momentum that appear there is denoted by 4 plus n. And because the Hamiltonian is like an energy density, the dimension of the Hamiltonian is 4 powers of the energy. So that means that higher dimension operators have the suppression, which is lambda to the power of n. So this, and C sub n is a low energy constant. That is something that you have to fix by using data. You solve the Schrodinger equation with this Hamiltonian, and then you try to determine what these coefficients C1, 2, 3, etc. are by fitting to, say, scattering data, or to, if you have binding energies, you fit to binding energies, and you determine these low energy coefficients. So in general, this would be the strategy to build a low energy theory. And now, whenever you're a Hamiltonian with higher dimension operators, with n, where n is greater than, say, 2, then you'll immediately see that you can't solve the Schrodinger equation because the Schrodinger equation will blow up, because when you do the integrals over momenta, if you're solving the Schrodinger equation in momentum space, will all diverge. And so you need also, in addition to specifying the Hamiltonian, you need to regulate these divergent integrals. So in other words, if you say, well, I'm just going to cut off the integral at a large momentum, let me choose 1 GeV, for example, for nuclear interactions, to cut the integrals off at 1 GeV, then you will see that the low energy coefficients Cn that you obtain depend on this cutoff. So, but the physics, the scattering cross sections or the binding energies should not depend on the cutoff. So this regulation scheme should be in such a way that the coefficient should be able to change in a way smoothly to preserve that the physical parameters don't change when you change this the scheme by which you regulate the integrals, the divergent integrals that appear when you try to solve something like the Schrodinger equation. So a low energy effective theory has two important ingredients. It has a very general momentum expansion or operator expansion of the Hamiltonian. So you're not leaving out anything. And in that sense, it's model independent. And it's a momentum expansion in the sense that you have even though this expansion contains infinite number of terms, you should see that at low momentum, compared to lambda, it should be adequate to keep just the lower order terms, and the higher order terms must make a small contribution to any observable. And the second part is, every low energy theory, you have to specify how are you regulating these divergent integrals, and that's called the renormalization scheme. Okay. Now, a specific low energy theory is called chiral effective field theory, and that is described that has been used to study nucleon-nucleon interactions. And so what we're going to do in the next, say, 4 or 5 minutes is discuss the chiral effective interactions, and then we can take maybe a 5 or 10 minute break, come back later. So this general idea of low energy interactions has been used to describe nuclear physics. And what this does is, we know that at long distances, the forces have to be induced by pions, and at short distances, they have to be induced by these contact interactions. So if I was to organize the operators that appear in the Hamiltonian in powers of the momentum Q divided by the scale lambda, so in chiral effective field theory, the breakdown scale of this effective theory is called lambda chi. And we expect this lambda chi to be of order, I don't know, 600 or 700 MeV, because the heavier mesons have masses of order 600 or 700 MeV. The scale has to be determined by fitting to experiment, but we expect this to be of order 600 or 700 MeV. So if at leading order means the operators that contain Q over lambda to the 0th power, so the 2 nucleon force is given by the pion exchange and 1 contact interaction. So there's 1 low energy constant associated with the contact interaction. So all you would get at leading order, which is shown in the figure on the right, is a contact interaction and pion exchange. And you would go fit, for example, the very low energy cross section of 2 neutrons to determine what that low energy coefficient should be. When you go to the next order, which is Q over lambda squared, it is now Q over lambda q over lambda to the first power, those violate certain symmetries so that those are not contained in the Lagrangian. And you have now a very complex set of diagrams that you have to include to calculate the potential. So in addition to the contact interaction, there's a derivative of the contact interaction that introduces a new coefficient. Then there's the 2 pion coupling to a nucleon. So there's now, as you go up in every order, you start having to fit many new parameters in the Hamiltonian to describe the physics. One interesting thing that you can notice is when you go to NNLO, that's the next to leading order in this expansion Q over lambda, you see that there are 3 body forces that arise in the theory. So this is a very important aspect of the low energy theory, because any low energy theory between many particles will always contain many body forces. And if there's no way to separate many body forces from 2 body forces, then you have a poorly defined theory. But if you can show that many body forces appear at higher order in the expansion, that's good news, because then it tells you that as long as the momentum is small, even in a system containing many particles, you don't have to worry too much about these many body forces. And that is a very important aspect of any theory of many particle systems. Because if you have a theory in which the 3 body force is not small compared to the 2 body force, then you don't know if you have a reasonable description of the theory, because your 4 body force and your 5 body force, all of these may be equally important. So chiral EFT shows clearly that there is a hierarchy of these many body forces, and that at low momentum, 2 body forces must be more important than 3 body forces. Now, this is the most important aspect of a low energy effective theory. It says that if I want to calculate an observable, let's say I take 10 neutrons, I put it in a box, and I want to calculate its energy. So if I was to just take the simplest part of the Hamiltonian, which is the leading order Hamiltonian, and I calculate the energy, I will get an answer. And then I can say, let me estimate how big the error can be. And there are many ways in which you can estimate this error. For example, you can take a higher order operator from NLO and calculate its expectation value. And you can see how big is the error. And you can estimate the error associated with the leading order calculation. And it basically says, if I was to calculate the next order at this momentum, how much of a contribution can I get? And that allows you to get an error bar for the leading order estimate. You can then do the same thing at next to leading order, estimate what next to leading order contributions could be, and calculate an error bar. And you can continue doing this to the point where you're convinced yourself that this expansion in terms of operators is actually converging for your observable. So if you see this pattern of convergence, it tells you that as you go to the next order, you get an improved estimate, but the estimate is always contained within the previous calculation. So the next to leading order result here has a smaller error, and it's consistent with the leading order calculation. So once you can establish this, then you have established that your answers are not sensitive to the short distance physics anymore. So this error estimation is the crucial ingredient in effective field theories, and that's something that we will discuss, after the break, when we want to talk about how do we use this to describe neutron matter that's relevant for neutron stars. So let's take a break. If you have questions now, I'm happy to take them. If you'd like to take a break, think about it and come. Good question. So so let's look at the layer between the outer crust and the inner crust. The outer crust and the inner crust is a smooth, it's more or less a smooth transition. The type of nucleus changes when you go from one region to another. Even inside the outer crust, you can have little transitions where you go from, say, iron to nickel or more neutron rich. So there can be small differences in the density when you go from one type of nucleus to another. But the transition, say from the inner crust to the outer core, that can have a density discontinuity. So we don't know whether or not there's a density discontinuity between the outer core and the, say, the quark-hadron transition. That depends on whether the phase transition is first order or second order. If the phase transition is first order, then there can be a big jump in the density. Otherwise, it's relatively smooth. Okay, so that's an important point you bring up. So if you think about low density matter, in the previous lecture, I told you guys that there's a first order phase transition between the QCD vacuum and nuclear matter. But even though it's a phase transition at zero temperature, it doesn't have the quantum critical behavior that you expect from second order phase transitions that one is more accustomed to in condensed matter physics. What's happening is that you have a state, you go from zero baryon number to a state with finite baryon number, but because of this electromagnetic forces, I showed you that even though it's a first order phase transition, it's a first order phase transition in two charges, the electric charge and the baryon number charge. So that complicates the picture very significantly compared to quantum critical phase transitions where you just have one charge and you have a second order phase transition. So that's why you don't have criticality in that sense at low density. Okay, so let's proceed. We just discussed the nuclear interactions. So we write down, at least when the nucleons can be treated as non-relativistic particles, we can write down a Hamiltonian. And this Hamiltonian we discussed contains potential, and the potential itself contains many operators. And these operators come with different powers of momentum if I was to write down the potential or the Hamiltonian in momentum space. So there is the two-body potential between nucleons. It may contain many operators at a given orders. You can constrain all of the coefficients of these operators by fitting to the scattering between two nucleons. And we have a lot of data, so that all of the operators that appear, say, up to some order in the effective theory or in some model where you don't have an organizational principle, but you have a function, you can fit the parameters fairly well with scattering data. Now, you also have these three-body forces. You could have four-body forces and so on. And the general method to try and fix those is to fit to light nuclei. So you can look at the binding energy of helium. You can look at the binding energy of triton and try to solve the Schrodinger equation for 3 and 4 particle systems and fit those coefficients in the potential. It turns out that the two-body phase shifts are very accurate, so you know a lot about the two-body forces. The three-body potentials are not as well constrained as the two-body potentials, so there's a certain amount of uncertainty associated with these three-body forces. So if I'm interested now in using this Hamiltonian to calculate the properties of neutron matter, which is important for astrophysics, then I need to specify what is the method I'm going to use to solve this Hamiltonian, to go from the Hamiltonian to the energy per particle. So that's what is called quantum many-body theory. So give me a Hamiltonian, and I have to specify a method by which I calculate physical observables like energies, pressures, etc. So typically what people have been doing in this field is to use broadly speaking, there are two methods. One is a computational method called quantum Monte Carlo, and that I'll describe in a moment. And the other methods called diagrammatic methods, which are based in some form of perturbation theory. So let's start with the simplest way of approaching this problem using a method called many-body perturbation theory. So what you do is you basically have 2 and say 3-body interactions, and you decide that you can write down diagrams. So given a Hamiltonian, and you write down the Hamiltonian in the second quantized form, you can start writing diagrams. You can represent different terms that appear as contributions to the energy, depending on how many times you insert a potential. So you organize the calculation in terms of these diagrams. Each diagram has an algebraic expression associated with it. So the leading order, just a diagram in which you just have a fermion, like say this, let's assume that we are doing this calculation for neutron matter. The solid line is just a fermion propagating. So that's just a neutron propagating, and there's a simple expression, that's the expression E kinetic that gives you the Fermi energy of a non-interacting Fermi gas. And then you put in a potential between two neutrons, and that will give you the first correction. We call this the Hartree-Fock correction to the energy of the system because of one insertion of this potential. So one insertion of the potential, which is shown here, gives rise to an algebraic expression that says that you have to look at all the particles in the system, calculate the matrix element between the two particles which are in a momentum eigenstate. So this symbol here, 1, 2, for the state of the particle just means that you have a neutron and two neutrons. One neutron has momentum k1, another neutron has momentum k2. You calculate this matrix element, and then you sample over all possible states in the system. So the momenta go from zero momentum to the Fermi momentum of the neutrons. And so this way you can calculate the corrections at first order insertion of the potential. You can say, well, you know, maybe the potential is not very weak. I have to insert the potential twice, and then you can calculate with two potential insertions. This should be there's a typo here. This should be a square. Then you start getting terms that look like the second order correction to the energy. So you can organize your if these potential insertions are small, in other words, they are perturbative, then you can just write down this expansion in terms of more and more diagrams and try to see if there is some kind of convergence pattern that you observe. Of course, if V is very small, it's going to make a very small correction to the kinetic energy. But you can have V that is not very small, but still which converges rapidly. And that's just something that one can examine by explicit calculation. So although there is no small expansion parameter if V is moderate size, sometimes you can see convergence. You can't prove it, but you can see convergence that may lead you to believe that including a few orders in perturbation theory is adequate to get the right answer. Now, three-body forces can also be included in the same way. That's shown in the right column there. So if you had a three-body force, you write down a similar expression where you insert these three-body forces between particles, and then you sample over all the states in there. There's an important distinction between first-order corrections and second-order corrections. If you look at the second-order correction term written there, you see that it has all of these energy denominators that arise, and it also has a final state particle. So here you have nk1, that's the distribution of k1, nk2, that's the distribution of k2. These other particles, these are holes created in the Fermi sea. And so what you're doing is you're doing an integral over momenta. If you examine this integral, the first integral is convergent. So even if the integral were to go, these integrals just go from 0 to the Fermi momentum because those are the only particles you have. In the second integral, the integral goes over all momenta. So one of these momenta can be very large, well beyond that of the Fermi surface. And in this case, you begin to recognize that at second order in the calculation, the short distance behavior of this potential or the high momentum components of this potential become important. And so whatever scheme that you have to regulate these integrals is going to be very important. So when you calculate the energy of the particle at second order, you have to check to make sure that if you're using a theory, it's not very sensitive to the short distance physics. So people have tried to do these calculations to verify whether or not perturbation theory works. And, there is still some controversy as to whether or not this is a good approach to understanding strong interactions, and that's shown by this plot here. So if you try to calculate the energy per particle of symmetric nuclear matter, that's a state of matter that we know. We discussed that in the previous lecture. We know that the symmetric saturation point for symmetric matter is shown by this box, which is called as the empirical saturation point. So we expect nuclear matter, equal numbers of neutrons and protons, to saturate at this point and have an energy of order minus 16 MeV. Now, if you just did the first order calculation, which is called for Hartree-Fock, using a potential that fits scattering data, and so essentially what one is using is different cutoffs. So this is what I mentioned earlier, that you have to specify how to regulate these integrals when you do this calculation. And ideally, you don't want any dependence on the regulator when you do this calculation. However, clearly, when you do the first order calculation, you're not at all sensitive to the short distance physics. So even a small change in the cutoff function leads to large changes in the answer that you get. So at Hartree-Fock, there seems to be no convergence even with respect to the cutoff. And what one sees when you go to, say, second order in the calculation where you introduce two interactions, you see that all of these curves collapse very quickly to a single curve, and it's almost independent of the regulation that you see, regulator changing from about 1.8 Fermi inverse to about 2.8 Fermi inverse. That's something about 400 MeV momenta, all the way to about 600 MeV momenta. So now, yeah. Yeah, so I'm going to come to that in just a moment. So if you look at the second order calculation for this potential, you see that the second order calculation is what I described earlier. But the point that Ignatius Bombace is talking about is there are some diagrams that are important. That means that you have to resum some diagrams, not just do a naive calculation of number of insertions. There may be diagrams with infinite number of insertions of the potential that are important. One such insertion is called the ladder diagram. So you basically have two particles interacting with each other over and over again, and those are now an infinite class of diagrams that one has to include in the calculation. And when you do that, that's shown in the last panel. So the second order perturbation theory for these potentials seems to give the same answer as including all the ladders that would be in a theory that resums these diagrams to all order. So for this potential, it looks like perturbation theory seems to be working. But when you extend, if you try to calculate the same properties at larger cutoffs, beyond about 600 MeV, so a lambda, say 3.5 inverse Fermi, then you start seeing important differences between these calculations. So what this means is that perturbation theory appears to work if you have a regulation scheme that is very soft. In other words, if you cut off your momentum integrals at small values, then it appears that the second order contribution already provides the answer. But of course, we want our answers to be independent of this cutoff, which means that we have to go to some method where you sum a class of diagrams, or maybe have a strategy that includes all diagrams to ensure that your answer is independent of the cutoff. Nevertheless, the fact that you have this perturbative series converging to almost the correct answer for a class of theories with small cutoffs is promising. Provided you can prove that when you go to large cutoff, you still are within the same region of interest, or you predict the same energy even at these higher cutoffs. So that means that we should, in addition to many-body perturbation theory, it's important to include other non-perturbative effects. And so this is, in general, one can think of these as resummed diagrammatic methods, which means instead of having a systematic expansion in which you count the number of times you put the potential in these diagrams, you say that, well, I know some diagrams are very important. And I know these are important because when I try to calculate the scattering between two nucleons, these diagrams play a very important role. And that is the basis of theories which are known as Bruckner theory of dense matter or G-matrix theory of dense matter. And what you do in this case, for example, is you want to calculate a diagram in which two nucleons interact. They can interact by exchanging, arbitrary number of potentials. Here, the nucleon-nucleon potential is just represented by a dashed line. So you include arbitrary numbers of these, and you try to see if you can arrange them in a series that you can actually sum mathematically. So you cannot count all diagrams. These methods are always approximations. They count certain classes of diagrams where there's a mathematical formula that allows you to sum a whole class of diagrams. And one such method is Bruckner theory. And for example, in Bruckner theory, the scattering between two particles can be calculated to all orders in this ladder sum. And there's an algebraic expression or an integral equation that relates the scattering amplitude for two nucleons to all orders. And this can also be used to calculate the energy per particle. So for example, when you go back to this figure, the last panel of this figure where you say you've summed all the PP ladders, summing all the PP ladders is really equivalent to doing something like a Bruckner theory where you sum all the ladder diagrams together. Okay, is there a way in which we can actually do this, calculate this problem exactly? We don't know of any analytic way of doing this. There is one method called quantum Monte Carlo, which has been used very successfully to study non-perturbative problems. So if you want to really solve the problem without making any approximations on how many times you insert the potential, then you need to have a computational scheme that allows you to calculate the wave function. So this is now the first quantized version of quantum mechanics. So this is going back to the picture where you try to generate a wave function rather than calculate diagrams. So what you would like to do is you have a Hamiltonian and you have a many-body wave function, and you guess the many-body wave function, and you introduce parameters into the many-body wave function. And these parameters, you vary these parameters using the variational principle to minimize the energy. So let's say that you had a wave function that contained n Gaussians. Each Gaussian has some parameter. You try to change this parameter in the wave function, the shape of the distance. For example, the probability to find two nucleons at a certain distance could be an element of the wave function. And you guess the wave function, and when you do that, it's called variational Monte Carlo. So that's a little bit of an art in the sense that you need to have a wave function and you need to parameterize the wave function in terms of some functions, some parameters that you change, whose values you change to minimize the energy. Now, we would like to do better than that. And that means that you can start with a wave function that comes from this variational Monte Carlo method, and then actually find a systematic way to improve the wave function. And that can be done using a method called Green's function Monte Carlo. So you take a variational wave function and you act on the variational wave function with an operator that is e to the minus h0 minus e0 tau. And so when you act on that wave function with something like that, you can think of the general wave function as a wave function that contains a superposition of all states of the n particle system. It can contain the ground state, the excited state, and so on. However, if you act on an eigenstate of the system with this e to the minus h tau, as a function of time, what's going to happen is that all the excited states will have, and tau is a real number, and tau is called imaginary time. Because if this was a regular Hamiltonian evolution, you would have tau equals IT in the time evolution. So when you act on the wave function with this e to the minus IH tau, as you keep increasing tau, all of the excited state components in the wave function will get suppressed. So if this procedure can be done in a systematic way, then for large imaginary time, you will recover the ground state of the system. And so this method is called Green's function Monte Carlo. And practically the way you do it is you take n particles, you put it in a box, each particle has a coordinate, and then you move these coordinates in a way that is done through Monte Carlo sampling. So you evolve the coordinate locations, then you Monte Carlo the kinetic terms, and then you calculate explicitly the potential energy. And mathematically, this is quite tricky to do, and that's, you know, the actual evolution of the coordinates as a function of imaginary time is shown by this expression here, where this function g that takes you from n to n minus 1 is called the Green's function of this evolution. Now, in principle, this is an exact method, but it turns out for fermions, this is not exact because there is a problem with trying to evolve this for large time. So for very large imaginary time, you don't end up with the ground state, but you in fact end up with large fluctuations because of something known as the sign problem. And you may have heard about this from other lecturers. I don't want to go into the details of this, but this is a technical problem that one encounters when using Monte Carlo methods. But usually in practice, you don't really have to go to very large time to get useful answers. What one actually finds is that for moderate values of time, of imaginary time, before the sign problem kicks in, you get answers that are meaningful. And there's a lot of literature on trying to get the energy of a few for a gas of few particles from using these Monte Carlo methods. So what's useful is now people have used these Hamiltonians, done many-body perturbation theory calculations, done Bruckner theory calculations, also done quantum Monte Carlo calculations, and all of these together have started providing us a good sense of the energy of a gas of neutrons. And this is really interesting because all of these different methods for treating the Hamiltonian are all converging to the same point. So right now, the situation is not that we don't know how to solve the many-body problem. It looks like the many-body problem is, at least the different approaches are giving the same answer. The real challenge at the moment is trying to understand the Hamiltonian. How big are the errors? Because the nucleon-nucleon interaction Hamiltonian is not very well known. So calculations of the neutron matter using effective field theory-based Hamiltonians, and whether it's Bruckner theory or many-body perturbation theory or quantum Monte Carlo, all give results that are consistent with each other, and there are two important trends that we see in it. So up to a density of about 0.16 Fermi to the minus 3, so that's about 2.5 times 10 to the 14 grams per centimeter cube inside the neutron star. So this is a little bit into the outer core of the neutron star. The convergence of all of these results is very good. So we can calculate the energy of a neutron. So what's shown in this plot is the energy of a neutron using different potentials, all calculated using quantum Monte Carlo. These are results obtained by Ingo Hughes recently. And there is an ambiguity in the three-body forces, and the ambiguity in the three-body forces is not fully understood at the moment. And this leads to a large error in the calculation at high density. But the error bars still seem reasonable in the sense that the improvement when you go from leading order to next to leading order to next to leading order, that improvement exists. And that improvement, that type of convergence is very good at 0.16 Fermi to the -3, and up to about twice 0.16 Fermi to the -3, this seems reasonable. So if we were to ask ourselves how high in density can we calculate the equation of state of hadronic matter, the answer appears to be about twice nuclear density. Up to about twice nuclear density, we can calculate it using different many-body approaches. They all seem to have give the same answer, and the answers are shown on this plot here. So this is the energy per particle of neutron matter as a function of density. So at nuclear density, the energy per particle is uncertain by about 3 MeV out of 15 MeV. At twice nuclear density, the uncertainty is much larger. The uncertainty is about 15 MeV with a central value of 30. The pressure can also be calculated. The pressure at nuclear density is 2.5 MeV per Fermi cube, plus or minus 1. And at twice nuclear density, where the theory is now just beginning to start, the error bars are beginning to grow very rapidly, as you can see, and at this point the pressure is about uncertain by about 5 MeV per Fermi cube. So what we are doing now then is we can parameterize the equation of state of neutron matter based on all of these calculations, and what one finds is that in fact, after all these difficult calculations are done, the final expressions you get for the equation of state are actually quite simple. And the energy per particle, so the energy density is just given by this expression here, where energy density is equal to total number density of neutrons times the mass of the neutron plus the energy that we saw, energy per particle. And then the pressure is calculated as using this expression, which is n squared, the differential of the energy per particle with respect to density. So all of these calculations of the equation of state of neutron matter can be parameterized in this incredibly simple formula with only 4 coefficients. N is the density of matter, N0 is the density of, is 0.16 Fermi minus 3, that's the saturation density of nuclear matter. A, alpha, B, beta are fit to the microscopic calculations. And A and alpha are well determined because they mostly depend on the low density behavior where two-body interactions dominate. B and beta are more uncertain because they depend on the 2- and 3-body interactions at higher momenta, and the uncertainties associated with the chiral expansion become important. So if we are if you're interested in studying neutron stars, this is the information that we would like to include in calculating properties of neutron stars. So all the hard work of quantum many-body physics and the Hamiltonians is all contained inside these coefficients, B and beta especially, and the errors in B and beta characterize the uncertainty associated with nuclear interactions as you go to higher momenta. Okay, so are there any questions about what we just discussed? Okay, so of course we would like to make sure that there's some experimental information about neutron matter, and as I said in the first lecture, we have some information about a quantity called the symmetry energy, which is the energy difference between neutron matter energy and nuclear matter energy, and we said that that was about 32 MeV, and we also have information about this parameter L, which I discussed in the first lecture, which tells us how quickly this energy difference between neutron matter and nuclear matter changes with density, that parameter L. So you can relate this parameter S and L to the neutron matter calculations through A, B, and beta. So essentially what you can deduce is that if you know values of S and L to some uncertainty from experiment, then it provides constraints on A, B, alpha, and beta that would test the theoretical calculations of neutron matter. So the way you get information about S and L is shown in this plot here. And what you're seeing in this plot is, let me maybe figure out a way. So what you're seeing in this plot, let me just try to share this. Last time I tried to share this, it caused some problems, but let's just try this. So what you're looking in this plot is the nuclear masses in yellow. Heavy ion, some of the heavy ion experiments provide some constraints for S and L shown by the green curves. Measurements of the neutron skin provide the constraints shown by the blue curves. Excitations in a nucleus where you have neutrons and protons oscillating against each other provide constraints shown by the red curve. In general, the experimental constraints on L are not very good. As you can tell, it seems to move, values from about, say, 20 all the way up to 60 or 70 MeV are allowed. And the theoretical predictions from the different ab initio calculations are shown by these, by the small box, diagonal box called theory. So in addition, it turns out we will now learn that the neutron star radius, for example, is very sensitive to L. And this is something, for example, if the neutron star radius was 12 plus or minus 1 kilometers, then it tells us something about how big L can be. And we'll come back to discussing how does this sensitivity arise between the neutron star radius and this L parameter. So neutron matter calculations are at the moment much more sensitive to neutron properties of dense neutron matter than experiments. And maybe this will change in the future where experimental information about neutron-rich matter will actually provide us some direct constraints. But for now, we want to use these neutron matter calculations up to twice nuclear density to learn something about neutron stars. Okay, so we now are going to make a transition to study the structure of compact objects. All of the emphasis until now was on understanding the equation of state of matter, and now we have to see how the equation of state of matter determines the structure, the mass, and radius of neutron stars. So before we discuss neutron stars, I thought it'll be useful to understand the basic physics of compact degenerate objects. Again, this is something that I'm sure many of you have seen before, are familiar with, but it helps to go through this simple exercise. So if I was to ask you to estimate the size or the mass-radius relationship of a white dwarf, what would you do? You would start by first saying, well, my white dwarf is a compact star where it's very low temperature, so I can ignore the temperature of the white dwarf. And it's a state of matter in which you have ions, say some kind of nucleus. Maybe we can think of this as iron, or iron white dwarf made of iron nuclei and degenerate electrons. And you know that the ions are heavy. They don't contribute much to the energy increase in energy if you were to compress the system. So the first thing you would calculate is the kinetic energy of the electrons. So if I was to compress the white dwarf, something about its internal energy must increase. And this increase in the internal energy is what is going to prevent the white dwarf from collapsing. So the two energies, just like we did when we did the calculation of the size of the atom, we identified the two important energies in the system. In the size of the atom, it was the kinetic energy of the electron and the potential energy of the electron, in which case it was just the electrostatic energy. But for the white dwarf, we can do something very similar. We can just say, hey, let's assume that the white dwarf is a constant density object. If it's a constant density object, I can calculate the kinetic energy of the object. And when you calculate the kinetic energy of the electrons, you know that an electron gas has kinetic energy of order 3/5 pf squared over 2me. So that's where pf is the electron Fermi energy in the white dwarf. And since we are saying that the white dwarf is a constant density object, the Fermi momentum is the same everywhere inside the white dwarf. And you can then relate the Fermi momentum of the electron to the number of electrons in the white dwarf and the size of the white dwarf, because it's just the fact that the electron has to live inside the white dwarf. It tells you that the Fermi momentum of the electron is related to the density of electrons, and the smaller the white dwarf, the larger is the density of electrons. So using that, you can very quickly see that the Fermi momentum of the electron should go like 1 over the radius of the white dwarf. So the other energy for a white dwarf is the potential energy associated with the gravitational potential. So I can combine the kinetic energy and the potential energy and write the total energy of the white dwarf in this way. So you have a kinetic energy term, which is positive, and you have a potential energy term that is negative. So if I want to now just say what is the optimal size of the white dwarf, all I have to do is I have to differentiate the energy with respect to R. What is the size that minimizes the total energy, and set that equal to 0. And that gives me an expression that relates the mass of the white dwarf to the radius of the white dwarf. And that relationship is shown here in the bottom left. And I've written the relationship between mass and radius, M and R, using some very unusual units. And I did this for a specific purpose. Of course, 81 pi squared over 16, that's just some number that comes out from doing this, solving this equation. Then there's Z over A. Z is the charge of the ion. A is the mass of the ion, mass number of the ion. It goes to the 5th power. Instead of writing the gravitational, Newtonian gravitational constant, I decided to write it in terms of the Planck mass, because the Newton's constant is inversely proportional to the Planck mass squared. So MPL is the Planck mass. And then instead of writing the mass of the electron that appears in the formula, I've decided to write it in terms of the Compton wavelength of the electron. So if I now look at this formula, it tells me that the mass of a white dwarf goes like the radius to the inverse 3 powers of the object. So the mass radius of a white dwarf is given by this very simple formula in this estimate. And you can try to put some numbers in, and you see that the mass goes like radius to the -3 power for example, iron white dwarf, where the electron fraction is 1/2, you find that 0.7 solar mass white dwarf will have a radius of order 10,000 kilometers. So this is a simple exercise. It allows us to find the relationship between the mass and radius of a non-relativistic white dwarf. And if you do the full calculation, if you do a realistic calculation, you will find slightly different numbers, but you will find the same dependence between mass and radius. So this, an important aspect of compact objects is that as the radius of the object increases, the mass decreases as 1 over r cubed. Okay. So now you can say, well, what about relativistic white dwarfs? The only difference between a non-relativistic white dwarf and a relativistic white dwarf is that the energy per particle, or the energy density of electrons for relativistic particles, goes like the Fermi momentum rather than the Fermi momentum squared. So you do the same exercise. You now write down the total energy of a relativistic white dwarf, and then you optimize the radius. And when you do this, you find this result, which is has been a surprising result since the 1920s, which says that the mass of a relativistic, a fully relativistic white dwarf is independent of its radius. What this really means is that when you change the radius of the object, the mass doesn't change, and that is a sign of an instability. So it turns out that when you have a mass that is slightly larger than this critical mass, there is no, gravity wins and the object collapses. So this limit, which is called the Chandrasekhar limit, can be derived by just using this very simple estimate. And in this case, you get that the Chandrasekhar limit is 6.8 times YE squared, where YE is the fraction of electrons. For iron, it's about a half. For most ions, it's about a half times the mass of the sun. If you did this calculation correctly, instead of assuming that the white dwarf had constant density, you get a better estimate. Instead of 6.8, you end up getting 5.8 when you do the full calculation. And when you plug in